All right, let's go ahead and take a look at a few more examples of equilibrium calculations. The question is, will you use ice or do you not need ice? So that's something that you need to determine by looking at the problem. So decide if you need an ice table or not. So everything you need is here. The temperature doesn't make a difference in the setup for the calculation. So go ahead and calculate the equilibrium concentration of PCl3. All the substances in this system are gases. Go ahead and pause and do that now. All right, so this one, we already have equilibrium concentrations and we already have our equilibrium constant. So we don't need an ice table, just rearrange. So I start off with my equilibrium expression, K equals concentration of PCl5 over concentration of PCl3 times Cl2. Rearrange that to isolate concentration of PCl3, plugged in my values, and I get 0.00207 molar. All right, let's take a look at this next one. For this reaction, equilibrium constant is 0.771 at some temperature. 1.00 moles of H2 and 1.00 moles of CO2 are placed in a 5-liter container and are permitted to react as shown above. What will be the equilibrium concentrations of all 4 gases? All right, so a couple things on this one. First of all, make sure that when you plug in values to the ice table, it is concentrations. You can use moles, but this causes a lot of problems because students forget to convert to molarity before, say, plugging into their equilibrium expression. So I prefer you, if possible, to use molarities in your ice table, though it is possible to use moles. You could also use pressures, but we're going to stick here with molarities. This one's a little bit different, so I'm going to give you a chance to set it up. If you get stuck, go ahead and resume the video and I'll give you a hint and then I will let you finish that problem. So go ahead and pause now and see what you can do. All right, so here's what we have with the information given to us in the problem. So again, I took the 1 mole of H2 and 1 mole of CO2 and converted those to molarity. So 1.00 mole over 5.00 liters is 0.200 molar. Initial concentration of CO and H2O are both 0. And this one's a little different because we're given the value of K. So sometimes we've been asked to calculate the value of K, but this time we're given the value of K, and we're going to try to use that to find equilibrium concentrations. So we know the concentration of this will decrease, this will also decrease, this will increase, and this will increase, and we know that they will change by the same amount because of the 1-to-1 ratios for everything. But how much will the concentrations of H2 and CO2 go down by? We don't have any information. We're not given any of the equilibrium concentrations like we were in previous problems. And so we don't know. And so we need to find that. So instead of using numbers, we're going to use variables. So we have no numbers to plug into our C row. Use variables and then plug in those equilibrium concentrations that have variables in them into your equilibrium expression and solve for X. All right, try that out, and then I will finish the problem. For those of you that think you know what you're doing, you can check your answers. Go ahead and pause now and finish the problem. All right, so continuing on in the setup, here's what we have after I plug in my equilibrium concentrations. And so looks like we can factor out that bottom. We don't need to do that. If we do that, we're going to end up with a quadratic equation, which is fine, but we'd have to use a quadratic formula to solve for X, which is also fine, but we can simplify this. So how can we simplify this setup and make it easier to solve for X? So we're going to square root both sides. So go ahead and square root both sides and solve for X. Pause the video and we'll check answers. All right, so once we simplify, we get X over 0.200 minus X equals 0.878. and then solve for x. Ultimately, we get 0.0937. So x happens to be our equilibrium concentrations of CO and H2O. So 0.0937 molar, don't forget your units there. And then I plugged in x here to find the equilibrium concentrations of H2 and CO2. So 0.200 minus 0.0937 is 0.106, so 0.106 molar for H2 and CO2. So a little different problem. All right, let's take a look at another one. We have the equation for the reaction producing methanol, CH3OH. Everything that you need is given to you in this problem. This time we are not given the equilibrium constant, so we are going to calculate it. So this is not like the last problem. Once again, we're given moles of each substance. We're also given the volume of the container, so we want to use molarities when we do our calculations. Go ahead and pause and set that up. All right, so again, this, I guess, as well, and this were given to us in the problem. So we have 0.1000 moles in a 1 liter container, so 0.1000 molar for the CO. H2 was 0.2000 molar. No methanol at the very beginning, so that's a 0 there. And then it tells us at equilibrium we have 0.0791 moles of CO. So equilibrium concentration of CO 0.0791. So from here, I went here. So if you started with 0.1000 molar and at equilibrium you have 0.0791 molar, that means the concentration went down by 0.0209. And then from here, I went here using mole ratio. So if CO's concentration goes by 0.0209, concentration of H2 will go down by twice that amount, so 0.0418. And then I went to here. So concentration of the CH3OH will go up by the same amount that CO is going down by, because we have a 1-to-1 ratio. And then I went here, and I went here. So I got my equilibrium concentrations, plug them into the equilibrium expression. Don't forget about that square there, very easy to do. And so we end up with 10.6. All right, that concludes our lesson for now on equilibrium calculations. Next time we'll talk about the solubility product constant. Thanks for watching.